Okay, so this is the last topic for our what we may call as the first part of the course, which is the front-end design. And from next lecture onwards, we'll start with the MOS transistor and see how we can implement some of the things that we have been discussing using the MOS transistor here. So last lecture, we were looking at logic simulation. And we said that logic simulation, for it to be efficient, we should carry out the simulation of the different gates on the basis of the events. If an event has occurred on the inputs of any of the gates, we simulate it. Otherwise, we don't. And if we keep on doing it in a systematic manner, we end up simulating the circuit and in an efficient manner, in the sense that for each input vector, instead of simulating all the n gates, we may end up simulating only a small fraction of the gates. We also saw that in the process, the way the algorithm works, you may end up simulating one gate more than once, but it doesn't really matter because the number of gates simulated are small. And we also saw that in order to, the logic simulation is being done in order to verify the correctness of the logic. That's one aim. And in order to do that, one may want to do a multi-valued logic simulation. This shows a 5-valued logic simulation. As I was telling you, in the VHDL, you have all these different logic possibilities that are there. So the simulation of a gate is not in terms of simply binary inputs, but the inputs could be more complex, and some of these are given here. And if you want to verify, if you want to look at the timing aspects, then you'll have to include the delays of each individual gates, and then the simulation proceeds according to the delays. And as I was telling, the simulation with delays becomes more time consuming because of the computation associated with the delays. And so if we look at, if you want to verify whether the functionality of the circuit is correct or not, then this is what you do. Event-driven logic simulation, and you don't bother too much about delays at that stage, and you exercise your circuit with different input vectors, look at the outputs and see whether the outputs are what you have intended. And so you verify by applying a variety of input vectors here, large number of input vectors, and verify. If you want to verify, we also know that we would like our circuit to run at certain speeds. For example, this is simply a combinational circuit, but I could have a flip-flop here, and all these things, I1 and I2, could also be coming from a flip-flop. And so therefore, I would like to know what is the highest clock period that I can run. And for that, I need to know the what is the slowest path, for example, in this particular circuit. So in order to decide at what clock I can operate my circuit, I need to know the delays in my circuit. And delay estimation using logic simulation is very time consuming. As an example, let's say, if you have a combinational circuit, what is the worst case delay from input to output? Well, through simulation, what you would do is, if I have 20 inputs and certain number of outputs here, if you do exhaustive logic simulation, it will require 2 to the power 20, all possible combinations you give here, 10 to the power 6 simulation. So if you want to find out what is the worst case path, the brute force approach would be to apply all possible input vectors, find out after how much time does the output become available, determine all the delays, rank all the delays, find out the largest delay that is there here. Now, if you're thinking, well, isn't 20 inputs too large? Now, think about, you have 8-bit adders, 16-bit adders, 32-bit adders, these multipliers and all that. These are not large inputs. 20 inputs is not large. Anyway, that's only a combinational circuit. The other one is, what if it's a sequential circuit? Which in most of the cases it is. Sequential circuit with 10 flip-flops. Each one of these flip-flops could be in 2 possible states, 1 or 0. And for each state of the flip-flop, right, so 10 flip-flops are there, How many states are possible? 2 to the power 10. Each flip-flop could be 0 or 1. And so 2 to the power 10 states are possible. For each state of the flip-flop, each state of the memory, I can apply 2 to the power 20 input vectors. For each state of the flip-flop, I may apply 2 to the power 20 because 20 inputs are there. I may apply 2 to the power 20. So I approach a number which is 1 billion. And remember, when you are, and then of course I'll have to rank all of them and find out which is the worst case path. And remember, timing analysis will have to be carried out several times. Because you design something, you analyze it, and you find that your circuit does not meet the timing constraints. And therefore, you'll go ahead and modify something in your circuit, redo the timing analysis. Maybe again it doesn't work. Redo it again. So, several iterations may be required. So it's not something that you do at once. And therefore, what we need is simulation is not a feasible way of determining what is the worst case delay. Simulation is too slow. These simple examples themselves illustrate that you need huge number of vectors. What we need is an alternative method to predict the timing. And this alternative method is what we call as static timing analysis. Static, the word is coming because I'm not simulating it. I'm not simulating the circuit and looking at how the signal is propagating and all that, but I'm still doing timing analysis here. So the idea is, in the first case, we'll talk about something simpler, which is how do I determine the worst case delay in a circuit without any simulation? Okay. So the basic idea is the following. What we do is the circuit that is there is transformed into a graph. And the problem then becomes a mathematical one. How do I find the longest path in a graph? So take the circuit, transform it into a graph. Well, how do I do that? Here is the circuit. We'll do it systematically. Here is the circuit. We transform it into a path like this. A path from some source node to a terminal node. And then the problem is more of mathematics as to how to find the longest path in the particular circuit here. So how do I find that out? Okay, so let's do that here. So before that, note that the graph has two things in it. The graph has nodes in a graph, and there are edges. And along with the edges, we have a weight attached with it. So it's what we call as a weighted graph. Okay, so what are the nodes? The nodes in the graph are all the inputs and outputs of all the gates. Okay, the edges of the graphs are the connections between the gates and between the inputs and the gates. Okay, all right. So let's go ahead and start with it. So what we do is, in our circuit, we define first of all so let's say these are the delays associated with my 0.8 here, 1.38, 1 delays associated with the gate that are there. So we start with a source node. We define a source node. Everything starts from source and will end in a unique node called terminal node. So we start with the source node, and the other nodes are the inputs here, x1, x2, x3. Okay, so these are the nodes here, x1, x2, x3. All right, and what are the edges between source? So this is a artificial dummy node that we have defined. It's not there in the circuit, if you note. It's just that we have defined a starting point. And from source to x1, the edges are all with 0 delay because we don't have anything before x1. Okay, so it's just, as I said, it's a dummy node, starting node here. So we can go from source to x1, source to x2, source to x3, and the weight that I've attached is all zeros. Okay. Now note what are the other nodes in my circuit here? Nodes are also the outputs of the gates. So for example, if I define a node called A, what is A? A is the output of this inverter. A is the output of this inverter. And we can go from X2 to A. Note that from X2 to A we can go, right? There is a connection here. And we go through the gate. And therefore, as we go through the gate, we encounter a delay of 0.8. So we connect the fact that there is a connection between X2 and A through this inverter. So we put an edge here. And we attach a weight to that particular edge. And that weight is 0.8. Which is a delay associated with that particular gate. All right. So similarly, you can see here B. The output of this particular gate is B. And I can, of course, go from X1 to B. and I attach a weight 1.38, which is a delay here. And I can also go from A to B here. So I also attach an edge here, A to B, and a weight is 1.38. Now at this stage we have something simpler. Normally the delay from this input to the output would be different from delay from this input to the output. As we will see when we start implementing the gates in the form of transistors, you'll see the delays are different. It's not that each one of those inputs are identical. Okay, but for this case, let's say simpler. So from here to here, 1.38. Another node that we can define is C, the output of this particular one. And C is connected via, as you can see, I can go from the output A here to the C via an edge 1. And I can also go from X3 to C via another, there's a connection 1 here. And like that, then I can define D here, connect it up, define F here, connect it up, and finally, and then define E here, connect it up. And finally, everything ends at a terminal node we define, one last node here, and we connect it up with 0 edge. Alright, so the whole thing, as you can see here, the whole circuit has been transformed into a graph. And now what, and all the delays are there in this particular graph here. And so what I need to do is find out now what is the longest path by adding up all the weights that you see here. What is the longest path in my circuit? Now at this stage, I'm sure there's a little bit of a problem that you may see. I've taken a circuit and transformed into a graph. What is the information that has been lost? Some information has been lost now. Very crucial information has been lost in the process. Suppose between X2 and A, right? I had whether it's an inverter or a NAND gate or an XOR gate or whatever, that information is no longer there in my graph. Between A and B, as I go from A to B, what is that? Suppose I put this as a NAND gate, it would still have been the same graph. So the information about the nature of the gates is lost. Information about the nature of the gates is now lost. So now that, I'll just show you an example later on. Now I may end up finding a worst case path in my circuit, right? But it may be possible that there is no input vector for which that worst case path is activated. That is a real possibility. I may find the worst case path, but that worst case path never gets activated for no input combination. Okay, so we may end up getting something called a false path. So once I find a slowest path, then that's a potential issue. Okay, so what I just want to tell you is that at this stage, we have lost information about the gates here. But anyway, let's proceed. How do I find the longest path in my circuit here? Let's say the worst case path. So what we do is the worst case path is determined by computing a value called maximum arrival time at each node. At each particular node, I determine a quantity called MAT. And at each particular node, while I compute the MAT, I also attach with MAT what is the worst case predecessor, which means that, okay, if the maximum arrival time at B, let's say is some unit, the input that is coming to B, is it coming from A or X1? How does the maximum arrival time occur at B? Does it occur via the route A or does it occur via the route X1? Okay, so that's the other information that I keep in my, while I process my graph here. All right, so MAT B, for example, maximum arrival time at B would be maximum arrival time at X1 plus 1.38, the edge here, or maximum arrival time at A plus 1.38, right? These are the three possibilities of maximum arrival time at B. So now to compute maximum arrival time at B, I need to know maximum arrival time at X1, or I need to know maximum arrival time at A. So what you see here is that you have to compute the maximum arrival times in a particular sequence. I can't determine maximum arrival time at B unless I know maximum arrival time at A or at X1. So I have to compute at a proper sequence. And that sequence is what we call as, and of course we'll compare the two, and let's say this comes out to be higher. So we will know the maximum arrival time at B, and we'll also know that the worst case predecessor is A. Right? So we'll keep that. So what we need to do is, in order to compute, we need to do computation in a particular manner. So what we do is, we saw it earlier, we levelize a circuit. We divide a circuit into levels. Okay, so it's obvious, level 0 here, I can't compute any of these values unless I know the previous levels here. So this is straightforward. We divide it up into level 0, level 1, level 2, and level 6 here. So what are we going to do? Compute maximum arrival time for each one of these nodes, and starting from level 0 to level 6 here. Okay, that's what we're going to do. So that's straightforward. Maximum arrival time at S is obviously 0. There is no worst case predecessor here, so it's S only. Maximum arrival time at X1, X2, X3 is also 0, and the worst case predecessor is S. Is S here. Maximum arrival time at A is 0.8, and straightforward worst case predecessor is X2. Maximum arrival time at C is 1, worst case predecessor is X3. At B, well, at B we have a choice now. Maximum arrival time at B is 1 point. Maximum arrival time for C will be, yeah, so there is an issue here. C, it should be 1.8, and the worst case predecessor is A, right? So good. So maximum arrival time at B is, then you, anyway, you can fill it up, right? All right, so you know the idea, you fill it up, and once you know that, maybe I mixed up two examples, I think. So I had some other example and some things I here. So anyway, so you fill up this table. Maximum arrival time at each particular node in a systematic manner, starting from level 0 to level 6. So the first thing that we get is the delay, maximum delay. Once you arrive at that particular point here, you get the maximum delay, which is 3.98. And you also get the path. How do I get the path? You start with 3.98, and it says the worst case predecessor is E. So you go back E here. And then when you come here, E, the worst case predecessor for E is D. So you come here D, and the worst case predecessor for D is B. And then you come here at B, worst case predecessor is A, and you come at A, worst case predecessor is X2, and then back. So if you retrace your path back, you end up getting, I hope this is correct, you end up getting the path also. And so we can identify what the path in my circuit is. All right, so that's how you end up finding the, taking a circuit, transforming it into a weighted graph, computing, levelizing the circuit, computing maximum arrival times at each one of those nodes, starting from the level 0 to level 6 here. At the end of it, when you reach the terminal node, you have the worst case delay here. You have the worst case delay here, and then if you follow it back, because you've also kept track of the worst case predecessor, where is this signal, worst case E, and back and forth. If you start from here, you end up getting the worst case path through your circuit. All right, so that's the method by which we can identify. But that's not the end of it. Normally, what we also do is, so I find out the worst case path in my circuit. What we also do is, we will be given normally a timing constraint from a design. And therefore, what we try to do is, from the specified timing constraint, let's say I'm given that my signal should arrive at the terminal node T. We found a value 3.98. Suppose I find that the timing constraint is that the signal should arrive at T within 3.5 nanoseconds. So I'm given that constraint. So from the 3.5 nanoseconds, what I can do is, I can start from 3.5 nanoseconds here and compute the time required for, the required time at each one of those nodes from the timing constraint given by the user. So let me illustrate. So if 3.5 is the required time here, so I can go back, start from here, and systematically go back and compute the time required at each one of those nodes. So if this is 3.5, the required time at this is 3.5, 2.7, and we can go back and compute all of these here. Now I can look at the following. I have maximum arrival time at each node, and I have the required times at each one of these nodes, and I can start comparing the two here. Okay, so let's do that here. Maximum arrival time we have already determined. The required time are here, and I take the difference of the two. The difference of the two is what we call as a slack. The difference of the two is the following. Now, why is this information important? Because if the slack is positive, which means my design meets the timing constraint. If it's positive, it meets the timing constraint, and therefore is fine. But at this stage, even if it meets the timing constraint, if you find, let's say, for the sake of argument, we find here, let's say D was, required time was, let's say the opposite, 3.5 here, and required time was 3.98. And so the difference was, let's say, 0.48. So what it says is slack at this particular point is 0.48. Now, it meets the timing, but remember what you can do is, if the slack is 0.48, you may have used a much larger size of the NAND gate in order to, whatever, in your initial design, in order to lessen the delay here. Generally, you will see as you increase the size of a gate, its delay goes down. Okay, so at this stage, what you may do is, if you have used a much larger size for the NAND gate here, and you see there is a positive slack of 0.48, you may go ahead and decrease the size of the NAND gate here, because there is a very large margin, 0.48, let's say, which is there here. So you can intervene in your design and then modify the sizes of the transistors. You can take advantage of this particular information. But in our case, things are now problematic, in the sense that we are not meeting the timing constraint here. The slacks are minus 0.48 here at this stage E. F is not a problem. Slack is positive, 1.7. So again, if you've used a very large inverter, well, 1.7 here, you can go ahead and decrease the size of the inverter. And still, there would be no problem in your circuit. But anyway, let's come back here. Minus 0.48 here. So you can see the negative points that are there in your circuit. So now the issue is my timing analysis. All right. So anyway, so let me come. I'll come back to it. So I was commenting that that you lose information about the gates, and there is a possibility that what you may get is a false path here. So look at this example here, trivial example. So if you do static timing analysis on a circuit like this, it will indicate with all the delays that this is the worst case path, the red one. The red one is the worst case path in my circuit here. But you can clearly see that this worst case path will never be activated. To activate this particular path, I need a 1 here. Only if there is a 1 here, the signal will propagate, right? In an AND gate here. If you have a 1 here, 1 will go and automatically set it to 0. 1 in a NOR gate will set it to 0. Right? So what we are saying is that this path will never be activated. But your static timing analysis will give you this path. Right? Will give you this particular path. And so looking at it, after seeing a path, you may want to do some logic simulation and see whether that particular path can be activated or not. Anyway, let me come back to the other issue that was there. The worst case path I found out. Let's not worry about the false path for a moment. The worst case path I have found out in my circuit. But what I'm trying to tell you is the worst case path is not enough. It's not enough to know the worst case paths. Let's see the following here. This was the circuit, and the worst case path that we found was here. Okay, the worst case path that we found here, and the worst case path's value is 3 plus 2 plus 7 nanosecond here. And let's say for the sake of argument, my timing constraint is 6.5 nanosecond. Right? So now Now remember, what your timing analysis will give you is this worst case path that will give. So the information that you will have this, you won't have all the circuit available and the complicated circuit that is there, right? So we have this information available. You can see a worst case path that is there, 7 nanoseconds. So you try to intervene now. Suppose the only information I have is the worst case path. So now I try to intervene in my circuit and try to modify, try to meet the timing constraint. So from 7 nanosecond to 6.5 nanosecond. So what I do is, okay, let me intervene here and somehow reduce the delay of this block to 1.5 nanosecond, right? So now I see 1.5, 3 and 2, 6.5. So I'll be very happy I've met the constraint, right? I've gone ahead and remember that this may be a more complicated block. It may not just be a gate, all right? So I redesign it and I make it 1.5. So I'm thinking that I've met the constraint because I've already found the worst case path in my circuit, and that worst case path from 7, I've reduced it to 6.5, right? So now I redo the static timing analysis. So I redo it, and what do I find? This is the worst case path now. And the value of this worst case path is 6.9. Right? So I spent time, intervened and modified it. The worst case path is only 6.9. I only achieved a 0.1 nanosecond saving. Right? So now again, remember what I will get is, I may decide, well, 1.5, so my intervention here was not right. Okay? So I go back to my original stage here. So intervention here was not right. So I may say, well, let me modify at the beginning. Right? Let me intervene and modify to 1.5 nanosecond. Again, I would see, perhaps this is there, 6.5 nanosecond. Again, I simulate. And I modified it here, and this becomes 1 point here, and the timing becomes 6.7 nanosecond. So what is the message from all of this? The message is that the worst case path is not enough. I need to have information not just on the critical path, but also on the subcritical paths. The next one, not just the longest, but the second longest, and the third longest, and the fourth longest. At least say, several paths that I need to have. I need to look at them. Because if you intervene, you may keep going back and forth. You intervene here, and you find, well, you improve that particular path, but then something else becomes critical now. And that is 6.7 nanosecond here. All right, so what we are talking about is, you can see here, so what is happening is that you may have a critical path like this, P1, that you see here. This one, P1 here, starts from B and D and E here, P1. But you may also have another path which is subcritical, which branches off from here. Right, so this may be, let's say, the longest path, and this may be the second longest path. So what happens is we intervened at E, intervened at E and reduced the delay here, but then this path, nothing happened on this particular path. And let's say if the difference in the delay between these two paths was not very large, so you may improve this particular path, but then this particular path has not improved much. Or I can have a situation like this. I intervened here, let's say, but then there is a critical path like this, and there's another path which goes like this, here, joins it like this. And so I intervened here at B, and I improved it, but then it improved this particular part, didn't do anything here, and then this became the more critical one. So all that it is trying to do is that it's not just the critical path which is important, but the subcritical paths are also important. So your goal of static timing analysis is not just to determine the longest path, but a set of paths starting from the longest and the second and the third and the fourth longest. So what we need to do is, we want to find k number of longest paths in my graph here, okay? And so how do I find that? K number of longest paths in my circuit. Well, the brute force approach, as all of you know, will be untenable is what we call as the path enumeration. Enumerate all the paths that are there, right? All possible paths that are there, S to X1 to B to D. So you search your graph and you enumerate all the paths, P1, P2, P3, P4, P5, P6, determine all the delays, rank the top 10 of them that you're interested in, and you get the top 10 graphs here. The problem, as all of you know, well, you can see how to do the enumeration. The problem is the complexity is exponential, right? So we would like to find the top k paths one by one without enumerating all possible paths, right? Now, how do I do that? The worst case path was easy by calculating the maximum arrival time. But now I need to find out the top, let's say, in our simple case, we'll try to find the top 2 paths. All right. How do I do that? Okay. So what we do is the following. Let's look at the problem here. To find the top 2 paths, I start from S. Now the issue is, let's say I've already calculated the maximum arrival time at each one of these nodes. Is already there. So to find the top 2 paths, for example, so I would like to enumerate the paths starting from S to go to T. So the issue for me is, should I go along X1, X2, or X3 for the top 2 paths? Okay. So for that, what we do is, there is a parameter called esperance of the path. Let me explain what it is here. Esperance of a path is the sum of delay of the partial path and the maximum delay from the node to the terminal node T. So what we are saying is the following. For each node now, calculate maximum delay from that node to the terminal node T first. A parameter called, like earlier we had MAT, maximum arrival time. What we are talking about, maximum delay to the node, MDT. For each node, you can calculate what is the maximum delay from this node to the terminal node T. So compute that first. Okay, so let's do that first here, MDT. Maximum delay time to a node here. So the calculation is similar to, except that we start from the terminal node and work our way backwards. Again, the circuit is levelized. Maximum delay to node T, the first one is obviously 0. From E to T is 0. From here to here, you can work your way backwards, 0.8, 1.8. Maximum delay from C to T would be maximum delay at D plus 1 here, or maximum delay F plus 0.8. So you decide which one is which, and then you compute the value, 1.8. So you start from here, from the terminal node, work your way backwards and compute all the, I hope the calculations are right. So you work your way backwards and you calculate the maximum delay at each particular node. So this number is available to you. 0, 0.8, 1.8, all these numbers at each node is available to you. Okay. So what is this? Maximum delay, maximum possible delay from B to T is 1.8. Maximum delay from A to T is 3.18. So all this information you generate and you have it available here. So let's see how we can enumerate. So which node X1, X2 or X3 to choose for path propagation? Our task is to find the 2 longest paths here. So what are the possibilities? Consider propagation along X1. The partial path, so I want to know, should I go to X1 or X2 or X3? Okay. So partial path is 0 when I reach X1 here. And the MDT at that particular node is 3.18. So the esperance, that's what we call is, esperance of that particular path is 3.18. 0 plus 3.18. X1, the route to X1. The route to X2, esperance from S to X2 is, this is 0 plus 3.98. And route to X3 is 0 plus 2.8 here. So what I do is, these are the possibilities that are there available to me. I'm interested in the top 2 paths, so I choose the highest esperance, 3.98 and 3.18. Partial path, S to X2 and S to X1. These are the 2 things that I keep now. I reject S to X3. I don't need to search along that particular path here. Right? So S to X1 and X to X3. If I had more number of nodes, I would have computed esperance for all those things here and chosen the top 2. Okay? So I choose here these 2. Fine. So I have two partial paths, S to X1 and S to X2. Now I would like to propagate these paths. And at every choice that I get, I will calculate this esperance here. and make the decision whether to keep that path or reject that path on the basis of the esperance here. So let's see. So what I do is path P1, if you note here, path P1 is S to X1. So I propagate this particular path here. And in this case, it's a trivial example. As I propagate S to X1, X1 to B, I don't get any choices. B to D, no choices. D to E, no choices. I arrive at the final, at the terminal node. No choices are there along that particular path. So we have a path whose delay is 3.18. Fine. Let's look at the other one, S to X2. So S to X2, so we have a path P1, S to X2 here, is here. And we come to A. We come to A here, right? We come to A. At this S to X2, X2 to A, no problem. At A, we have a choice. Should I go along B or should I go along C? This is a choice here. B or C. If I go along B, the esperance of the path is 3.98. How did I calculate that? If I go along B, what is the delay up to B? X2, A, B, the delay is 0.8 plus 1.38 here. Plus the maximum delay from B to T is 1.8. So you add that up, you'll get 3.98. Sorry, what do you get? 3.18. S to X2 to A to B, 3.98 here, right? This is what you end up, 3.98. Or the other one, S to X2 to A to C, the esperance is 3.6. These are the two choices that you get here. So you calculate 3.98 and 3.6. And the previous path that we had already calculated was 3.18. So now I'm interested in the top two. So what should I do? Reject this one. This is no longer the one that I'm interested in. I should keep these two, P1 and P2. And then propagate P1 and P2. The top two paths is all that I'm interested in. If I were interested in top three, I would have kept this one also. So reject this and keep this. Because these are the two places, these are the two partial paths which will eventually become the two longest paths. So keep this here and then propagate. So this should have come earlier. Anyway. So now these are the two paths here, P1 and P2. So now propagate the first one, A to B. A to B, if you propagate, there's B to D, D to E, it will just become, there are no choices after that. So the first one you can propagate here, and it becomes a path, complete path, 3.98. That's one path now. Take the second option, S to X2 to A to C. At C, you will again get an option of D or F. Now, how do I choose? Again, from D, compute the esperance of this partial path. Compute the esperance of this partial path. Calculate that. Let's do that. So when you come to C here, you can go to D or F. Compute that. Esperance for the D path is 3.6. Esperance for the F path is 2.6 here. And we've already enumerated one path before. Right? One path before. So I'm going to reject this 2.6 here. One path earlier was full path 3.98. And the other path I'm going to keep 3.6. This path I'm going to reject. So 3.98 and 3.6 here. So top two paths are here. And so we end up calculating then is the following. Paths with the largest and the second largest delays are P1, which goes from S to X2 to A, B, D, E here, and A, C, D, E, E. So these are the two, the critical path, and this is the subcritical path. And by the same method, you can find out, so we kept track of only two. You can keep track of 3, 4, 5, the top 10 paths, top 15 paths. You can do that. And you'll end up getting all those subcritical paths. So if you do that, then what we were talking about is you will have information from static timing analysis about these also, these situations here. That there's a path like this, there's a path like this. So you'll have all these information. And then when you are intervening and modifying your circuit, you can do it in a more intelligent manner here. Because now what changes should I make so that it affects not just path P1. If you know this situation, you will never intervene at E1. You won't intervene at E, and you may want to intervene at B. But if you know that this is there, I've not drawn it together, P1, P2, and suppose P3 was also there. So you knew P1, and you knew P2, and you knew P3. So top 3 paths if you knew. Then you would know that it's not a good strategy to intervene at E, not a good strategy to intervene at B. D is the best place perhaps to intervene. Because D would then improve all the paths here. P1 also it will improve, P2 also it will improve, P3 will also improve here. So when you have information about all the top 10 of 20 or whatever paths, then you can make more intelligent decisions as to how to intervene and modify whatever lies on those particular paths in order to meet the timing constraints here. So the idea is in the simplest possible manner to tell you how this static timing analysis is carried out. The tools that are actually there, they may be doing things much more efficiently, but at the heart of all of this is that the circuit is transformed into a graph. Things like maximum arrival times, maximum delay to T, esperance, these are the concepts that are played with, and one arrives at the different paths that are there in your circuit here. As I said, once the paths are there, you may check whether that path is activated or not. You may try to find an input vector and see whether you can sensitize that particular path or not, and propagate things, and check whether the path is false or is a true path here, right? So we can. So this brings us, as I said, to the end of our the first part of this particular. We started with the introduction, of course, right? So you sort of the idea was to give you an overview what digital IC design is all about, if you recall. And you must have seen in that the whole idea was about the introduction was it's like in a very simplified way the map of the course. So you saw that there was some combinational design and all that, but you also saw that one has to do a transistor schematic and one has to do a layout. My design is only complete after I do a layout of my entire circuit. Using the layout information that you have given, the foundry will go and make a set of masks customized for your design, and then they can fabricate the circuit, right? So the end of the design is the layout. Now we've been talking about these delays that you see here, 1.38 and 0.8. Where would the delay come from? I mean, if you recall, what I've been saying is, let's say we have done an RTL design, multiplier. Take multiplier example, right? So I want to design a multiplier chip. So I choose an algorithm, and I do an RTL design, right? A data path and a controller. After I do a data path and a controller, then I have these blocks, registers and adders and all of those things that are there, and control unit. I convert all of them into a gate level, you know, and in the process we looked at logic synthesis. How do you minimize, and you do technology mapping and all that, and you have a gate level description here. But where is the delay? Where are these delays coming from? You started from the top, right? From the multiplier description, and you are systematically going, and you've arrived at the gate level description. Where do the delays come from? Huh? Gate has no information. Gate is just a block with two symbols, right? It has no information about delay. But I've not gone to the physical level, right? I've not gone. And I'm doing all this 1.38 and 0.8 and all that. Where is it coming from? But I've not gone to the transistor level, right? So what we are doing is top-down design, right? You start from the top, the specs, and gradually you do RTL and the gate level. So I've come to the gate level. But remember, I have a lot of choices to make at this stage, because if I'm not meeting timing constraints, I may have to decide, well, one adder is not enough, or I use a ripple carry adder. Ripple carry adder is not good enough. Look ahead carry adder. I may have to take a decision. How will I take those decisions? I must have delays. Where are these delays coming from then? I've not gone to... See, delay will eventually come from where? Delay will not come from... logic has no delay in it. A gate has no delay. Gate has absolutely... I mean, you know, it's a logical operation. It's a Boolean operation. Gate will... Delay only comes about because you have a capacitance and you have to charge and discharge. That's the only source of delay in your all these circuits. So the NAND gate will be made up of transistors. Transistors will have capacitances. Wires will have capacitances. And when you go from 0 to 1 or 1 to 0, the capacitors will have to be charged or discharged. Delays will come from there. So what am I putting here then? Where are all these things coming from? Well, these things are coming from because one route is that, let's say you have a design team. One team has already sat down and done all the basic gates, independent of your design, right? Has sat down and made a NAND gate with the transistor schematic and layout and everything. And they've done a NAND gate, they've not done a NOR gate, they've done a flip-flops and all that. So I've been showing you a library of gates. At various points of time, I showed you that this is from a 180 nanometer library. So I have elementary gates, elementary blocks whose design has already been done to the layout, right to the layout level. Right? So the elementary designs have all been done beforehand. And layout has been done and the delays have been characterized. So I have all the delays of my gates. So those delays are what I'm putting here. But there's a problem. There's a problem because if you go back and look at, for example, when I go from A to D, I have a delay of, let's say, inverter A, and a delay of this particular D. But when I connect A to D, there is a wire here. And the wire has capacitance in it. And the wire delays have become very important. Now that information I don't have. See, somebody has constructed a library of gates, elementary gates, they're giving me the values here. But in my design, between A and D, there is a wire sitting here. I don't have that wire delay available. Because that wire and its length is specific to my design. It's specific to my design. So at this stage, please realize that I don't have complete information about delays. I have some information. When I'm putting it here, I have some information, 1.38 and all that, but I don't have complete information. So it may happen that what we do is we do all of this here and we fix our timing. We fix our timing, but our delays are not complete at this stage. The complete value of delays when will they become available? After I get a transistor schematic, after I do the full layout, then I will know exactly how long is this wire between A and D. How long is this wire? And then from the length of the wire, I'll recompute the delay of my gate A, taking into account the length of the wire. Then I'll have a very good estimate of the delay of that particular inverter A. And I'll have to, at that point of time, I'll have to run timing analysis again. After doing the layout, I'll have to do a STA, static timing analysis. And I may find I'm not meeting the timing constraint. Right? So what do I do? If I'm not meeting the timing constraint, well, I can do something to the layout. But sometimes to the layout, you can't, no matter what you do to the layout, you can't fix it. You have to go back. You have to go back to the logic level or the RTL level and say, no, I have to use a carry look-ahead adder. I was trying to use a simple adder, I have to use a carry look-ahead adder. So design is never go in a nice linear manner to the end. It will never go like that. It is highly iterative unless you're doing a very routine design. That's something you've done earlier. Then your experience comes into picture. Otherwise, there'll be a lot of iterations. You'll have to go back and forth. Okay, so please remember, all these delay values are tentative. So it's very important that we go to the next stage. We start doing transistor level, start calculating delays and understand where these delays come from. Okay, all right.